So let us discuss the topic current electricity. In the previous topic, we have discussed the static electricity, in which we studied the charges at rest. Now in this topic, we introduce certain properties of the charge when it is under the motion. Now let us first define the current. Let's consider that some positive charge Q plus is moving in the forward direction through some area of cross section, and Q minus is the charge that is moving in the opposite direction. Now the net charge in the forward direction will be Q plus minus Q minus. So this net charge is directly proportional to T. Now we can define the current as the rate of flow of charge, that is Q net by T. This quantity is called the electric current. I represents the electric current. The unit of I must be coulomb per second, and this is named as ampere after the scientist Ampere. So the SI unit of current is I. The conventional direction of the current is from positive to negative, that is just opposite to the electronic direction of the current. In fact, if the electron is moving in this direction, this gives us the direction of the current. So this direction is called electronic current's direction, and this direction of the current is called conventional direction. The conventional direction is named just based on the flow of positive charge from one place to another place. So the direction of the positive charge is this, and the direction of the electrons is this. To be frank, in any substance, the transaction of the charge will always be taken place by virtue of moving the electrons only. So this is the direction of the flow of electrons, and opposite to that is considered as the direction of the flow of positive charge. Don't think that positive charge means protons will flow in one particular direction, because protons are associated within the nucleus. So the charge transaction is always done through electrons only. So this definition is valid when steady current is there. It's not possible that always the steady current is there. Therefore, to generalize the definition of the current, we write I is equal to delta Q by delta T. So here we take the limit of delta T as tending to 0. That means in a small interval of time, how much charge is passing through that particular area is only known as current. So here the amplitude of the current is represented in terms of, or rather SI unit of current is ampere. So that means it has magnitude, and the direction, it has got specific direction from positive to negative, but still it is not considered as a vector. Why? If you remember, to call any physical quantity as a vector, it is compulsory for us that it should have the direction, it should have the magnitude. Both these are there with the current. But vector law addition is also to be hold good if you want to call that particular quantity as a vector. In the case of current, it is observed that vector law addition is failed. That is, if the current, some current, let's suppose 5 ampere current is coming through this one, this path, and 3 amperes are coming to this path, then 8 amperes will be passing through this. But in case of vectors, had the current been a vector, it would not have been satisfied. So one should not be confused that current is a vector. So it is a non-vector quantity, even though it has direction and magnitude, but because it is not obeying the law of vector addition, it is not a vector. Now, to study more about the current, we must have some recapitulation of the structure of atom. So in the chapter structure of atom, we have studied within the atom nucleus is there, and around the nucleus the electrons will be moved, and within the nucleus neutrons and protons are there. So in substances there are some free electrons. These free electrons will only cause this electric current. But if you take a metal will have large number of free electrons, and it is called a conductor, which allows the flow of electrons, or which allows the flow of charge through it. But if you touch the metal, you do not receive any shock. Why? Because there is no current constituted. The free electrons will be moved in a very random direction. So whenever the free electrons are moved in very random direction, there is no velocity associated with it. Therefore, average velocity of the electron is 0. Now, how do you make these electrons to move in a specific direction, or how do you give the velocity to the electrons, or how the current can be constituted in a metallic conductor? So for that, you must apply a potential source. Let this be a conductor. If you apply a potential source like DC voltage source battery, then the electrons will have a specific motion in one direction. We have discussed initially all the electrons will be moving at random. There is no specific direction for the motion of the electrons. Therefore, the electron average velocity is considered to be 0. Now, as and when the potential source is connected across the metal or conductor, then immediately a positive, an electric field is generated. An electric field, the direction of the electric field is always from positive to negative. In the opposite direction of electric field, the electron will have a tendency to move. The velocity acquired by the electron when a potential source is applied opposite to electric field is named as drift velocity or drift speed. So now that all the electrons will have a tendency to move from in the opposite direction of electric field, that is negative to positive, and constitutes a current. So here this potential source will control the motion of these electrons. Therefore, if more potential difference is applied, the current is increased. If the lesser potential source is applied, the current is reduced. You can simply verify by connecting a bulb with a single battery and observe the brightness of the bulb. Let it be B1. Now the same bulb is connected across two cells, and if you observe the brightness of the bulb now, it is obvious that in the second case the bulb will have larger brightness. So it can be verified with a simple setup of bulb and a cell. That means here more is the potential, more is the current, because the brightness of the bulb is directly related to the current passing through the bulbs. So V is directly proportional to I. Or if you want to write with a constant, so V is equal to IR. So in fact we can verify this law, which is popularly known as Ohm's law. This Ohm's law can be verified by this method qualitatively, simply by observing the brightness of the bulbs. Now, what is Ohm's law? Let us state Ohm's law. George Simon Ohm is the full name of Mr. Ohm, and he has given this Ohm's law. The current passing through the conductor, I, is directly proportional to the potential applied across the two ends of the conductor when all physical factors like temperature and pressure remain constant. Let me repeat Ohm's law. At constant temperature and pressure, the current passing through the conductor is directly proportional to the potential difference applied across the two ends of the conductor. So this I is directly proportional to V. It is also accepted that V is directly proportional to I. If you want to make this equation proportionality constant, you have to multiply with a proportionality constant, and that proportionality constant is R. This R is known as resistance. So V is equal to IR or RI, or R is equal to V by I is the formula for Ohm's law. The SI unit of this resistance is ohm, which is equivalent to volt per ampere. Now, what is this resistance? What is the physical meaning of resistance and why it is caused? The literary meaning of resistance means to stop, to obstruct. Here, which is obstructing the flow of charge? We have discussed already that electrons will be moved in a random motion as long as there is no potential difference. Now, once the potential source is applied, then electrons will tend to move in a specific direction. So, while moving in a specific direction or while rearranging their motion in a specific direction, one electron will come with the collision of with another electron. So, the first reason for this resistance is collision between two electrons, that is electron and electron. The second cause, the collision between ions and electrons. Third, the collision between the electrons and bonds. So just like friction, this resistance will be opposing the flow of charge. More is the resistance, less is the current. So this resistance is basically caused because of these three: collision between two electrons, collision between ion and electron, collision between electrons and bonds. This resistance depends on certain factors. The factors on which the resistance depend are: 1. The length of the conductor, 1. Length of the conductor. More is the length, then more is the resistance. So this is the first statement. Now this resistance is inversely proportional to area of cross section of the conductor. This is second. Now if you combine these two statements, resistance is directly proportional to L by A. Or we can write an equation by writing a constant of proportionality rho, which is called the specific resistance or the resistivity. It is resistivity or specific resistance, rho L by A. Therefore, the resistance is equal to rho, the specific resistance or resistivity of a material, times length divided by the area of cross section. So R is equal to rho L by A. Now how do we define specific resistance? So specific resistance is nothing but RA by L. It is easy to define the specific resistance if you make the value of A and L to be 1. Then the resistance offered by a conductor having 1 meter length and 1 square meter area of cross section. Or you can understand, suppose if the current passes through two faces of a cube, two opposite faces of a cube, then the cube will offer some resistance, and that resistance is only known as specific resistance. So the resistance offered by this cube, remember the unit area of cross section and unit length. So this cube, whatever the resistance it offers, then that is only known as the specific resistance or resistivity. The SI unit of specific resistance or resistivity can be derived as RA by L or ohm, and A meter square divided by L, that is meter. Therefore ohm meter is the SI unit of specific resistance. You can find out this specific resistance of different materials, and the result will be different for different materials. Now this specific resistance is purely a property of that particular substance, that particular material. Therefore specific resistance will not be affected by changing the geometrical measurements like length and area of cross section. So specific resistance is always constant for a particular material, and it does not depend on the geometrical measurements, as resistance depend on the geometrical measurements like length and area of cross section. This specific resistance can be calculated with the help of an instrument called meter bridge. Later on we will come to know how to calculate the specific resistance or resistivity of a material by using the meter bridge. Now we started with Ohm's law.